Hey everyone, welcome to another explainer. Today, we're taking some pretty dense, intimidating chemistry notes and transforming them into your ultimate lab survival guide. You can kind of think of this as part cookbook, part detective agency. We're going to learn exactly how matter behaves, and more importantly, how to uncover its hidden secrets. Okay, let's dive right in by asking the ultimate forensic question. How can we confidently identify substances that we can't even see? I mean, you've probably wondered how chemists can just look at a beaker of totally clear liquid and know exactly what's swimming around in there, right? Well, it's not magic, it's methodology. And by the end of this explainer, you're going to know exactly how it's done. To crack this case, here's our agenda. We'll start with acids, bases, and neutralization. Then look at the recipes for making salts, move on to testing for chemical anions, and finish up by identifying mystery metal cations. Let's jump in. Section 1, Acids, Bases, and Neutralization. Let's set up the fundamental ground rules for our chemical kitchen. So this entire chemical system, it completely relies on the exchange of protons. An acid is essentially a proton donor. It dissociates in water to produce positively charged hydrogen ions. On the flip side, a base is a proton acceptor. It's really just one continuous transaction, with acids generously giving their protons away and bases stepping up to gladly accept them. Now, to actually see these invisible properties in action, we use a brilliantly simple tool, litmus paper. Acids will take damp blue litmus paper and instantly turn it red. Meanwhile, alkalis, which are really just water-soluble bases, do the exact reverse, taking damp red litmus paper and turning it blue. It's a super quick visual cue that tells us exactly what kind of proton transaction is going down in that beaker. But what actually happens when these two opposing forces meet? Well, they undergo neutralization. The hydrogen ions from the acid and the hydroxide ions from the alkali combine to form something completely harmless, water. The chemical tug-of-war just perfectly balances out. Moving to Section 2, Making salts and their preparation methods. Now that we know our basic ingredients, let's literally open up the cookbook. Looking directly at these original handwritten notes, the big takeaway here is that you can't just mix things randomly. Choosing your recipe depends entirely on one main factor, and that's the solubility of your reactants and your final products. So let's say your goal is to make an insoluble salt, one that is absolutely not going to dissolve. For that, you'll use the precipitation method. It's beautifully straightforward. Step 1, you just mix two soluble salt solutions together. Because your final product is insoluble, it instantly forms a solid, which we call a precipitate. Step 2, you just filter out that solid. Step 3, wash it with distilled water to get rid of any impurities. And step 4, dry it out. Boom! You've just cooked up your first insoluble salt. Okay, but what if we want to make a soluble salt, and we're starting with an insoluble base or metal? That's where we use the excess solid method. First, you add an excess amount of your solid reactant into a warm acid until literally no more dissolves. This just ensures every single drop of the acid has reacted. Second, you filter off that leftover unreacted solid. Third, you take the remaining liquid, your filtrate, and heat it up to its saturation point. And finally, you cool it down slowly. This slow cooling, that's the absolute secret sauce that allows for perfect crystallization, leaving you with these beautiful pure salt crystals. Our final recipe is the titration method. You use this exclusively when you're making a soluble salt from a soluble alkali and an acid. Since everything dissolves perfectly here, you can't just filter out the excess like we did in the last method. So step 1 requires some real precision. You use an indicator to find the exact neutral endpoint where the alkali and acid perfectly balance each other out. Step 2, you repeat those exact same volume measurements from your practice run, but this time without the indicator. Why? Well, leaving the indicator out allows us to obtain a perfectly pure, uncontaminated salt solution that's ready for crystallization. All right, Section 3, Testing anions. We've cooked up our salts, so now let's step into the interrogation room and run some qualitative tests to identify these chemical suspects. This table right here is your ultimate cheat sheet for identifying anions, the negatively charged ions. Look at how incredibly specific these tests are. If you suspect you've got a carbonate, you add dilute hydrochloric acid. The dead giveaway, gas bubbles that when you pass them through line water create a white precipitate. That tells you carbon dioxide is present. For a chloride anion, you add dilute nitric acid followed by aqueous silver nitrate. Bam, you get this dense white precipitate of silver chloride. And for a sulfate, dilute nitric acid plus aqueous barium nitrate yields an insoluble white precipitate of barium sulfate. By adding very specific reagent mixtures, we're essentially forcing these invisible ions to show themselves through highly distinct physical reactions. And this isn't just theory, by the way.
Whether you're testing municipal water purity or running a forensic analysis, these are the exact methods used to reveal precisely what's hiding in the water.
And finally, Section 4, Testing Cations. Let's complete our profile here by focusing on identifying the positively charged metals. The visual outputs here are just fantastic. When testing for cations, it is all about the colors. If you add warm aqueous sodium hydroxide and it liberates a gas that turns damp red litmus paper blue, you've found ammonium. But check out the metals. Adding aqueous ammonia dropwise to copper-2 creates this light blue precipitate that actually dissolves into a stunning deep blue solution if you add excess ammonia. Iron-2 reacts with aqueous sodium hydroxide to form a really distinctive green precipitate that won't dissolve in excess. And iron-3, under the exact same conditions, forms a reddish-brown precipitate. These striking colors make identifying the metal almost foolproof.
So I'm going to leave you with a quick puzzle to test your new detective skills. Imagine you're handed a mystery liquid in the lab. You discover that a gas liberating from it turns damp red litmus paper blue. Then you add sodium hydroxide to a fresh sample of it and you get a distinct reddish-brown precipitate. So who are our culprits? Well, based on the evidence we just uncovered in this explainer, you now have the exact playbook you need to piece together those clues, ID the ions, and solve this mystery. Keep analyzing, stay curious, and thanks so much for joining me.